Good day. I hope you are all fine. This is the last chapter of the syllabus, which is called Synchronous Machines. Now, please study page 259 to 268 in your Machines 3 handbook. There we will find that the pole pitch is the peripheral distance between two poles, which is tau p. It is always expressed in electrical degrees, and therefore tau p is 180 degrees electrical or pi radians. Then we get to the pitch factor. That gives us a reduction in the copper overhang, which means it's cheaper machines because less copper is used. Then also we get a reduction in harmonics in the generated EMF, and we almost get a sine wave output. Now let's look at the teeth. Now, from the beginning of the teeth to the beginning of the next teeth will be your pole pitch, or from the middle of the one tooth to the middle of the other tooth is the pole pitch, which is psi. And then there, as you can see, the full pitch coil is from the North Pole to the next South Pole. Now, a coil can be short pitched or over pitched. Now, if it's short pitched, that means it is less, the coil spans less than 180 degrees by an amount of epsilon. And for an over full pitch, it is more than 180 degrees and by epsilon degrees. So therefore the pitch factor Kp is cos of epsilon divided by 2. Now if we take harmonics into account, then Kp of the nth harmonic is equal to the cosine of n times epsilon divided by 2. That brings us to the distribution factor. Kd is the phase sum of the EMF in coil sides divided by the arithmetic sum of the EMFs. So Kd is sine G dash psi over 2 over G dash sine psi over 2. That is for the fundamental. If we include harmonics, then Kd at the nth harmonic is equal to sin n G dash psi over 2 divided by G dash sine epsilon over 2 psi. So there we have G dash is the number of slots per pole per phase of the coils wound. Psi is your electrical degrees between slots, and n is the order of the harmonic. So the winding factor is a product of the pitch factor and the distribution factor. So Kw is equal to Kp times Kd. For full pitch coils, Kp is equal to 1. The induced EMF is equal to 2,22 Kd Kp phi Znp volts per phase. If Z is in conductors, then we get 2,22 Kd. And if Z is in turns, then it becomes 4,44 Kd Kp. And then please study chapter 5 from page 268 to page 283. Now, if we look at exercise 8.1, number 1, Kd is equal to sine G dash psi over 2 over G dash sine psi over 2. Now, G is the number of slots per pole, and G dash is the number of slots per pole per phase. So G in this case is 180 degrees divided by the number of slots per pole. That gives us 15, and therefore G dash is 15 divided by, it should be 12, divided by 3 is 4. So Kd is 4 sine 15 divided by 2 over 4 sine 15 divided by 2, that gives us 0.958. Then number 2, we have P is equal to 4. N is 750 revs per minute. There's 72 slots, each having 10 conductors, and the flux is 0.1 Weber. And we have a full pitch coil. Now, see, in this case, we have 360 degrees divided by 72. That gives us 5 degrees mechanical. And Z is equal to 72 slots with 10 conductors. So that gives us 720 conductors in total. Remember, we are working per phase. Therefore, we divide by 3, which gives us 240 conductors per phase. So G dash is the slots per pole per phase. So that's 72 divided by 8 divided by 3, that gives us 3. And electrical degrees is P times mechanical degrees. So that means it'll be 4 times 5, which is 20 degrees. So therefore, KD is sine 3 times 20 divided by 2 divided by 3 sine C over 2, which gives us 0.9598. And then the induced EMF is 2,22 KD, KP, phi, ZPN. So that's 0.22 times 9.9598 times 1 times 0.1 times 750 divided by 60 times 4 times 240. That gives us 2556.89 volts. Okay, now you can do that exercise further on. Then if we look at the basic synchronous model, there you first have to study page 286 to 292. Then there we have the synchronous model where we have the excitation for the field, the induced EMF, the armature resistance, and leakage reactance, which is the sum of the synchronous reactance and the armature reactance voltage impedance. So therefore, we can say that E angle delta is V plus IA ZS angle beta plus or minus phi. And the voltage regulation is E minus V divided by V, or in per unit, it will be per unit minus 1. Now, if we look at the no-load characteristic, that is the variation of output voltage as a function of the excitation current when the alternator operates at synchronous speed with the armature terminals open circuit. Now, if you measure it, IF against V, then you get a characteristic curve like that. Then the short circuit characteristic, that is where we have short circuit at the output terminals, and we change the excitation, and with that we get a straight line curve. Now the voltage regulation can be determined by 2 methods, the synchronous method and the Rother's impedance MMF method. Now the synchronous impedance method is where we use the synchronous impedance, if that is known. So let's look at 3-phase 600 kVA 3300 volt alternator as a star connected stator. The resistance of the winding is 0.37 ohms and a synchronous impedance of 4.3 ohms per phase. Compute the voltage regulation for unity power factor, 0.8 power factor lagging, and 0.8 power factor leading, and draw the complete Phasor diagram. So first of all, we calculate the full load current, that is S divided by square root 3 V line, that gives us 104.973. And the impedance angle is R cos R over Z, which gives us 86.05. And there's the Phasor diagram. because for unity power factor, the voltage is in phase with the current, and therefore we get IR in phase with V, and that is the phasor diagram. Now, E angle T, angle delta is V plus IZ beta plus or minus phi. Always remember we are working per phase, so that's 3,300 divided by square root 3, which is 1905.26 at an angle 0, plus 104.973 at an angle 0 times the impedance, which is 4.3 times 86.05. That gives us a voltage of 1995.16 at an angle of 13.03 volts per phase. There you can see the phasor diagram for that. Just remember, IR is always in phase with the current caused by it. IX is perpendicular to that current, and where they join, we get IZS, and then therefore from the origin up to that point there is the induced EMF, and that is the load angle and the power factor angle. Now for a leading power factor, for a lagging one, is 1905.26, 104.973 at an angle of minus 36.87 times the impedance, 4.3 at an angle of 86.05. That gives us 2231.49, angle 8.7. And then lastly, for a leading power factor, is 1905.26 plus 104.97.973 at an angle plus 37 times your impedance 4.3 angle 86.05. That gives us a voltage of 1709.7 at an angle of 12 degrees. And there's your phasor diagram for that condition. The voltage regulation, case 1, 1995.16 minus 1905 divided by 1905 gives us 47.2%. For the second case, voltage regulation is 2231.49 minus 1905.26 divided by 1905.26. That gives us 17.1%. And then the voltage regulation for the last case is 1709.7 minus 1905.26 minus 1905.26. That gives us a negative 10.26 degree percentage. Now, let's have a look at this Rutherford's simple MMF method. There we need the open circuit and the short circuit characteristic, and the full load current can be determined by S is square root 3 volts V line I line, or P is equal to square root 3 V line I line cos phi. Then the Rutherford voltage is V plus IARA cos phi, all added arithmetically. The phasor sum of the excitation for Rutherford's method, the resultant MMF, F res, is F Roth, angle 0 plus F short circuit 90 plus or minus phi. Now, if you look at the phasor diagram for the MMF, the zero power factor, lagging, the short circuit MMF is direct opposition with the Rutherford MMF, and the resultant MMF, F res, is F Rutherford plus F short circuit angle 180. Now for a zero power factor leading, that means they are in phase, so F res is F Rutherford plus F short circuit. Now if you've got a lagging power factor, there you can see F res is F Rutherford plus F short circuit angle 90 plus phi. For a leading power factor, we have F res is F Rutherford plus F short circuit angle 90 plus phi. The short circuit ratio is the ratio of the excitation to give rated voltage on no load to the excitation to circulate full load current on short circuit. So R short circuit is F rated voltage no load divided by F short circuit full load, or can be expressed as 1 over X per unit. Let's look at an example. 220 volt, 40 amp, 50 hertz, 6 pole star connected alternator has a resistance of 0.6 ohms per phase. Compute the voltage regulation at a power factor of 0.8 lagging by means of the EMF method and then Rother's method. Those are the open circuit and short circuit values for the graphs. Remember, if nothing is said, it's given as line voltage. So first of all, you have to convert that to phase voltages. Then you draw a graph to determine the EMF for 40 amps. So there you put your excitation with your short circuit current, and there's 40 amps. And where it crosses your short circuit curve, you go straight up to your voltage EMF curve and go across and read off from there. Then it's 100 volts. So your impedance is V over I at the same excitation. That means it's 100 divided by 40 amps, so that gives us 2.5 ohm. Beta is cos R over Z. That gives us 88.63 degrees. So therefore ZS is 2.5 at an angle of 88.63 degrees. Used EMF is 220 divided by square root 3, which gives us 127.02 plus 40 at an angle minus 36.87 times 2.5 at an angle of 88.67. That gives us a voltage of 204.6 at an angle of 22.6 degrees. Voltage regulation is then 204.6 minus 127 divided by 127. That gives us a value of 61.08%. And this method is optimistic. Now, if we look at Rother's method, calculate E Rother is 127 plus 40 times 0.6 times 0.8. That gives us 128.92 degrees of volts. So if we now look at the graph, we find F res is F Rother plus F short circuit 90 minus 5. So for the Rother voltage, we go down on the graph and we find that it is 1.7 and 1.2 is given. So that's 1.2 plus 90 minus 36.87. That gives us a value of 2.604 at an angle 22 degrees. Then we go back to the graph. At 2.6, we go up straight till we cross the EMF, go right across, and we find that the voltage there is 163.5. So the voltage regulation then is 163.5 minus 127 divided by 127, and that gives us a 28.74% regulation, and that is pessimistic. Now the real voltage regulation lies somewhere between these two values. Now let's look at the power relationships. The developed power, which is inside the machine, is E times IA cos of the angle between E and I. Output is V times I naught cos of the angle between V and I naught. Now, if we use the equation for the induced EMF and we make I the subject of the formula, we get E over Z beta minus delta minus beta minus V over Z angle naught minus beta. Now, in all power relationships, we work with the conjugate of the current. Therefore, IA is ES over Z divided by beta minus phi minus VZ over beta minus angle 0. Now, if we draw a phasor diagram like that, we have E and V, and then EZ over and V over Z. So E over Z is an angle of beta, and the angle there is delta. And then V over Z gives us beta there. So P developed is E times IA cos of the angle between E and IA. Now, first of all, let's look at E and rotate anticlockwise. The first thing that we get is E over Z cos beta, and then V over Z cos beta plus delta, and that. So we have E over Z times E cos beta minus V cos beta plus delta watts per phase. The output power is V times IA cos of the angle between V and IA. Again, now we take V as a reference and rotate anticlockwise. The first one that we get is E over Z, and the angle there is beta minus delta. And V cos beta. Now Q is just sine theta. So therefore we have E over Z times E sine beta minus V sine beta plus delta. And the output power is V over Z E sine beta minus delta minus V sine beta. Now for a large machine, R tends to 0, and that means beta becomes close and actual 90 degrees. So then this simplifies to P developed is EV over X sine beta, and that is the same as the output power since I square R losses are now ignored. Q developed is E squared over X minus EV cos delta, and Q naught is V E over X sine delta minus V squared over X. Let's look at an example. A three-phase 5 kVA 208 volts 4-pole 50 Hz star-connected alternator has an impedance of 1 plus J8. Compute the active power and the reactive power for full load conditions for a lagging power factor of 0.8. So I float is 5,000 divided by square root 3 divided by 208. That gives us 13.9 amps. E is V plus IZ beta plus or minus phi. Phase voltage 100 plus 13.9 at an angle of minus 36.87 times 1 plus J8 gives us 195.261 at an angle 24. Now if we use the long formula, since we are given R, then we get to 1.7882 kilowatt per phase, which is 5.365. The output power, you can see there, is then 5 kilowatt. Q developed is 2.591 kVAR per phase or 7.74 kVAR. Q out is 512.24 volt ampere per phase, and which is 1.357 kVAR. Now, example 2, the same as the previous one, except that Z is now just reactance. Compare PD and QD, both methods. So I full load is 13.9, E is 188.969, and then P developed is EI cos of the angle between the two. That gives us 1.172 kilowatt per phase. Sorry, yeah, 112. And then if we use the formula, then we can get the same answer, 1112 watts per phase. which is 3.3037 kilowatts. Developed power, E, reactive power, EI, sine of the angle between E and I, gives us 2.38 kilovolt ampere per phase, or 71389. If we use the formula, then we get the same answers. Okay, now we are done. Thank you for all your attention. I'll see you during the test. Goodbye.